Welcome. In this video, we'll walk through solving an equation that might look a bit intimidating at first. Our goal is to find the value or values of x that satisfy this equation. The quantity x squared plus 1 over x squared, all squared, equals 64. The squared terms and fractions might seem tricky, but we'll use a powerful algebra technique to simplify this into a much more manageable form. By the end of this video, you will be able to solve complex-looking equations by identifying repeated structures and using substitution. Let's begin by observing our equation closely. Notice the expression inside the parentheses. We have x squared plus 1 over x squared. Our first objective is to simplify this part of the expression. The key here is to recognize a pattern from binomial expansion. Recall the formula for squaring a binomial. A plus b squared equals a squared plus 2, a b plus b squared. Let's see if we can force our expression to look like this. The x squared and the 1 over x squared seem to be our a and b squared terms. So we can rewrite the expression as x squared plus 1 over x squared plus 1. Now consider the binomial x plus 1 over x. What happens if we square it? Using the formula, x plus 1 over x squared is equal to x squared plus 2 times x times 1 over x plus 1 over x squared. Let's simplify that middle term. The x and the 1 over x cancel each other out, leaving us with x squared plus 2 plus 1 over x squared. Compare this result to the expression we're trying to simplify. X squared plus 1 over x squared plus 1. They are almost identical. Our original expression is just one less than the squared binomial. This means that x squared plus 1 over x squared plus 1 is the same as x plus 1 over x squared minus 1. This simplification is our first major step. Now that we've simplified the expression inside the parentheses, let's substitute it back into our original equation. Our original equation was the quantity x squared plus 1 over x squared, all squared, equals 64. Substituting our new simplified form, we get the quantity x plus 1 over x squared minus 1, all squared, equals 64. Look at that. We've removed the fractions from the inner part. To make this even easier to work with, we'll use a technique called substitution. This is an incredibly useful strategy for simplifying complex equations. Let's define a new variable. Let's say y, to represent the repeated expression, y equals x plus 1 over x. By the way, we're assuming here that x is not 0, otherwise 1 over x would be undefined. Now we can rewrite our entire equation in terms of y. The equation becomes the quantity y squared minus 1, all squared, equals 64. Notice how much cleaner and more familiar this equation looks. We've transformed a complicated-looking equation into a standard algebraic problem. We're almost there. We just need to solve for y and then use that to find x. Our simplified equation is the quantity y squared minus 1 squared equals 64. To get rid of the outer square, we can take the square root of both sides of the equation. This gives us y squared minus 1 equals the square root of 64. Remember, when taking the square root, we must consider both the positive and negative solutions. The square root of 64 is 8. This splits our problem into two separate cases. Let's solve them one by one. Case 1, y squared minus 1 equals positive 8. Case 2, y squared minus 1 equals negative 8. For case 1, we add 1 to both sides. This gives us y squared equals 9. Taking the square root, we find that y can be either positive 3 or negative 3. For case 2, we again add 1 to both sides. This gives us y squared equals negative 7. The square root of a negative number is not a real number. For this video, we'll focus only on real solutions for x, so we can ignore this case for now. So we have successfully solved for beta. Y, we found two real solutions, y equals 3 and y equals negative 3. Our next and final step is to use these y values to solve for x. We've arrived at our final step. We know that y equals x plus 1 over x, and we have two possible values for y. This means we have two separate equations to solve for x. Our first equation is x plus 1 over x equals 3. Our second equation is x plus 1 over x equals negative 3. Let's solve equation 1 first. To eliminate the fraction, we'll multiply every term in the equation by x. This gives us x squared plus 1 equals 3x. Rearranging this into standard quadratic form, we get x squared minus 3x plus 1 equals 0. This quadratic equation doesn't factor easily, so we'll use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Plugging in our values, ai equals 1, b equals negative 3, and c equals 1, we get x equals 3 plus or minus the square root of 5, all divided by 2. This gives us two real solutions for x. Now let's solve equation 2. The process is identical. Multiplying by x, we get x squared plus 1 equals negative 3x. In standard form, that's x squared plus 3x plus 1 equals 0. Using the quadratic formula again with a equals 1, b equals 3, and c equals 1, we get x equals negative 3 plus or minus the square root of 5, all divided by 2. This gives us two more real solutions for x. Combining our results, we find that there are four real values of x that solve the original equation. So let's quickly recap our journey to find x. We started with the equation, x2 plus 1 plus 1 x2 equals 64. Our main strategy was to simplify this by first spotting a connection to the binomial expansion of x plus 1 by 2. This allowed us to rewrite the expression inside the parentheses, getting rid of that pesky middle plus 1 term. Then to simplify things even further, we introduced a substitution y equals x plus 1 over x. This transformed our complex equation into a much more familiar one. 1.2 equals 64. We solved for y, which gave us two real solutions, 3 and negative 3. Finally, we substituted y back and solved the two resulting quadratic equations for x, finding a total of 4 real solutions. By breaking the problem down and using substitution, we were able to solve an equation that seemed daunting at first glance. I hope this video has shown you how these techniques can simplify complex algebraic problems. Thanks for watching.